Assalamualaikum student. Okay, I will proceed our lecture on the second session on the topic of mechanically stabilized reinforced retaining wall. Okay, so I will go to the slide presentation. Okay. Okay, we proceed on the general design consideration. Okay, to design for the mechanical stabilized retaining wall, so you have to check two parts. First is the internal stability, which you have to check for tension and pull out resistance. Okay, and then second one, you have to check for external stability, which are overturning, sliding, and bearing capacity failure. Okay, so this is the figure, shows this sliding. Okay, we don't want our wall to slide. Okay, and then we check for overturning, we don't want our wall to overturn. Okay, and then we check for bearing capacity, meaning that the ability of the soil to sustain the load. And then you have to check also the deep-seated stability. We don't want to have a huge slide of your wall. Okay. Okay. So the main component of the reinforced wall is the backfill. First is the backfill. Backfill, usually we use the granular soil. Okay, and then the second one, we have reinforcing strip. Okay, and then we have cover or skin of the wall. Okay, in front of the wall. So this figure shows the main component of your of the reinforced retaining wall. Okay, so here we have skin. Here we have skin. So skin, sometimes we use geotextile, or we can use also the precast concrete slab as a skin of the wall. Okay, and then we have backfill soil as a backfill. Okay, granular material, sand or other granular material. Okay, and then we have a tie, reinforcing strip. Okay, so the SH is the spacing between the reinforcing strip in horizontal. Okay, and then SV is the spacing between the metal strip in vertical, SV. Okay, so you have to familiar with the component. Yeah. So this photo shows the reinforced retaining wall. Okay, so we have skin here using the precast concrete slab here. Okay, and then we have the metal strip. Okay, and the backfill. Okay, so same goes to this figure. Okay, so this figure more clearer. So this is the precast concrete slab, and this is the metal strip. Okay, and then this is the granular material. Okay, okay, using this figure below, okay, we can determine the Rankine active pressure at any Z. Sigma A prime lah. Okay, equal to this equation. Okay, so you have to familiar with this figure. Okay, all the variable here, so you have to familiar, because as an engineer, when you design, so you have to determine, okay, what is SV, what is your SV, what is your H. H is the height of your retaining wall, okay, and the length of your metal strip. Okay, so this one is the surcharge lah here. Okay, yeah, surcharge. All right, meaning that as the you have additional loads lah on the top of your wall of your wall. Okay, so for the dry granular soil, yeah, with no surcharge, okay, given by this figure, okay, if there's no surcharge, so C prime equal to 0 because it is granular soil, so the C is 0, okay, and sigma 0 uh, equal to alpha gamma 1z. Okay, Ka equal to this equation. Okay, tangent this one lah. Okay, tangent square 45 plus phi 1 prime over 2. Okay, and then sigma A 1 prime equal to gamma ZKA, gamma 1 ZKA. Okay, and when surcharge added on top of the slope, yeah, on your reinforcement wall here, okay, when you have added surcharge here, so sigma not prime equal to this equation. Okay, so sigma not 1 prime is referred to the soil. Okay, this one is referred to the soil. Okay, surcharge due to the soil itself, the pressure due to the soil itself, and this one sigma 0 to prime. Okay, this one is due to the surcharge. Okay, okay, the magnitude of sigma 0 to prime can calculate using 2 to 1 method of the stress distribution. Okay, here 2 to 1 method lah. So to calculate for this one, okay, is given by this equation. Okay, the difference is the location of your surcharge. Okay, B prime. Okay, B prime is the edges of your retaining wall to the edges of your surcharge. Okay, so it's defined as B prime. Okay, so you can use either one of this equation. It depend on the Z and B, 2B. Okay, all right, and then another equation that you can use to calculate for sigma A2 prime is equal to this equation lah. Okay, and then the M here is given by this equation. All right, so you can calculate the M using this equation lah. All right, okay, so the tie force per unit length of the wall developed at any depth of Z can determine by this equation T equal to sigma A prime times SV SH. So this one is the active pressure at the depth Z. Yeah, yeah. We go through the equation just now here. Yeah, here. Yeah, to get the sigma A prime. Right? And then SV and SH is the area of wall to be supported by the tie, right? Okay, the reinforcement tie could fail due to tie breaking or tie pull out. So you have to check for the FOS against the tie breaking and also the tie pull out. So the FOS should more than 2.5. Usually the FOS you should get is more, the optimum is between 2.5 to 3 lah. Okay, so the equation to calculate for the factor of safety for the braking is given by this equation. here, right? Yeah. Okay. So yield or breaking strength of each tie over maximum force in any tie. So W is the width of each tie, okay, and T is the thickness of the each tie, and Fy is the yield or breaking strength of the tie material, right? And this is the equation to check for the factor of safety against pull up, yeah, at any depth of Z. Okay? So Fs P equal to this equation. All right. So LE is the effective length. Yeah? And sigma no pi is equal to effective vertical pressure at depth Z. Okay. And the phi mu prime equal to soil tie friction angle here, yeah? The variable here. All right. And then the total length of tie at any depth Z is given by this equation. L equal to LR plus LE. So LE given by this equation, okay? And then LR given by this equation. So you substitute LE and LR into this equation, so you get L, right? So the L is here in the figure here. Yeah, need this one. The length of your metal strip is L. So LR plus LE, right? So you get the L here, capital L here, right? Okay, I will proceed on the step by step of design procedure and also example in the next session. Okay, so we stop here. Okay, thank you, student. Stop sharing. Oops. Discard. And then we end our session first. Okay, we continue next session. Okay, bye.